we did the structural health monitoring, there are various kinds of tools which we have tried to use. Broadly, we started with wave propagation tool, and the basic problem which we looked into for damage detection was the corrosion. Next slide, please. So the corrosion, as we all understand, because all the damages which, except to loading, the basic problem in the RC structures is corrosion. So next, please, next slide. So this shows the ingress of the ions, and the basic mechanism is that when the corrosion happens, there are two kinds of reactions which takes place: the anodic and cathodic. The anodic reaction basically results in the pitting of the rebar, and the cathodic reaction, where the corrosion products that deposit on some other region of the rebar, they lead to the cracking and spalling of concrete. Now, two phenomena which basically the effect of corrosion is seen is that we see the cracks in the structure, and the load carrying capacity of the structure reduces because the reinforcement is subjected to pitting. Next, please. So when we use the various kinds of tools to assess the corrosion, these are the slides which just show that what are the effects. We have almost seen all of them. The rust product is very voluminous.
Excuse me, ma'am.
Yes.
Harsimran, you may please hide this pop-up at the bottom. Meet.google.com is showing your screen. Yeah. Thank you. Thank you.
Thank you. These are the effects of water and aggressive ions. They penetrate, leads to corrosion. Now, the corrosion product is so voluminous that it leads to the spalling and cracking of the surrounding concrete. The reinforcement bars are exposed, and finally, ultimate failure occurs. Now, people have been trying to inhibit the corrosion in various ways. You can delay the onset, but you cannot eliminate it completely. Next slide, Harsimran. Yes, so some people have tried to seal into those cracks by putting on epoxy agents, or maybe some grouts and some routing and sealing techniques, and they've also tried to repair with FRP. But these are very localized procedures which may not, totally give away the corrosion, or the corrosion may not completely stop. Next, please. So as I outlined, the onset can be delayed by some amount. But it starts, you cannot stop it. Various technologies, like people have been using self-healing compounds, corrosion inhibitors. They have tried to use polymer-based concretes, but these methods, they're not able to avoid the corrosion completely. Stainless steel bar use or epoxy coated bars used in place of the traditional bars can to somehow manage the corrosion, but you cannot stop it completely. So the idea is, next please, next, just click it once more. So again, these are some of the techniques that people have been using to repair and rehabilitate the corrosion affected structures. Next. So, but the cost is a very huge factor. Instead of rehabilitating this corrosion affected structures, what if we can arrest it at a very early stage, where we can detect the initiation of such corrosion affected or damages in structures, and timely repair and manage them or maintain them. We don't have to maybe go in for costly repairs. Next. So that's the key. There's one express article, financial, so that it's actually eating up the GDP. Corrosion, the cost of corrosion repair, maintenance, and the losses, it's causing a lot of but the burden on the fiscal. So it needs to be handled in a way that if we can somehow manage the initiation, pick up the initiation, and stop the progression at a stage where we do not have to rehabilitate or repair the structures. That should be the key focus. So people have been using various strategies to do that. Next slide, please. So acoustic emission is one such technique. Now, acoustic emission, it's a kind of a wave propagation technique wherein you listen to the noises inside the concrete which happen because of these cracks or damages. So it's just like, please click again, Harsimran. It's just like a doctor uses a stethoscope to listen to the signals inside our body. Similarly, we use the acoustic emission sensors. They are put on the structure whenever there is a damage which happens inside, which is not visible to you at a initial stage. The sensor listens to that stress wave, which is due to the release of energy cracking occurring. It listens to that, converts it into it converts into electrical signal, which we can somehow measure. So it's just like these sensors work as the devices which the doctors are using, like stethoscope, to get to know the health inside. So this A parameter, or the signal which we pick up, or it is converted into a signal, or a wave is converted into a signal. If we can, you can, we can understand how that signal changes as a result of this detection or of this damage. That can be related to the extent of the damage in the structure. Next slide. It's like acoustic word in itself means hearing inside what is happening inside before it comes up on the surface. So it listens to basically cracking inside, slipping. If we talk typically of RCC structure, it's a passive system. Why a passive, not an active? Like in normal impact echo or ultrasonic techniques, we are sending the signals or exciting them. That's the active method. Herein, we are just putting the sensor and listening to those noises which occur as a result of deformations. So it's a passive system. So if we talk in totality, a combination of the active and passive system would work very nicely. But there are some advantages and disadvantages of both of them. As I already said, because it gives you the insight of happening, what is happening inside the structure. So it has a capability to be extended to a real-time system. Next slide. So this is just an example that it's not something new. It has been there very long back. People have been, for example, a person crossing a bridge very long back. The creaking of the timber tells us that it's about to break. So these are some examples that it has been there since long. Next, please. And now we're trying to utilize into monitoring the health of our structures. A typical acoustic emission setup, what it looks like, there's an AE sensor put on the structure, and those sensors listen to the inside crackings or deformations or plastic deformations taking place. These signals are pre-amplified or they're amplified, and there's a processing unit, like a typical physical acoustic corporation unit, which converts this electrical signal into a signal which we see, and then we can the typical A signal from concrete, if you talk of, is of two types, either a continuous or a burst. In concrete, most common is the burst signal, which is shown on the right hand slide, a typical A signal from concrete. Now, looking at the various parameters like its peak amplitude, the number of times the peak crosses the threshold is called a count. So, by counting these events, we can tell what is the state of the inside of the structure. Next slide, please. So this slide shows various parameters which we look into, like the amplitude, peak amplitude. There is a threshold which we set before the sensors which are chosen for detecting damage. It will be different for different structures. Like steel will have some different kind of sensors. Means the frequencies are typically kilohertz to megahertz, 20 kilohertz to probably 1 megahertz. So the choice of a sensor is important, and when we choose a sensor, we typically see what kind of a material what kind of material is into which we are looking the defects at. So the some parameters like threshold is the one that it is the basic level below which we are not recording. So any signal which crosses this threshold is counted as an AE hit. So once you put the sensors on the screen, you will get these signals, and you will also see there is a hit, there is a record of an event or a AE hit. So all my sensors, if they typically pick up the event or the cracking inside, they'll show it as a hit. So some basic parameters which we look is peak amplitude, the hits, the counts, the number of times the AE signal exceeds the threshold, average frequency, rise time. So this is a typical waveform on the parameters which we look into. Like we'll see how we utilize it further. Next slide. So for typically corrosion detection or any kind of damage which occurs inside, wave propagation tools have been there since long. Active system wherein we send, this slide shows a beam which is subjected to accelerated corrosion being monitored using ultrasonic method. So it is what we are doing is we are sending the signals from a transmitter from one end and receiving the signals. So if there is any change inside happening in the steel bar, for example, this is a guided wave setup, ultrasonic guided wave setup. But then we'll come to know that we came to know that it has its own disadvantages. This will work only when it's an active system, but it works only when the damage has exceeded a particular limit. The change in the signal is not so dominated. It's not changing so drastically in the initial stages. Therein when the acoustic emission comes to our rescue. So the combination is like this: an active ultrasonic setup, for example, or even an impact echo. They may work at a later stage, but we don't want to miss the initiation or the onset of damage. So that is why we started looking for a passive system wherein the sensors are directly mounted onto the systems. So this is an active setup where we use low frequency. We'll show in the next slide how it didn't work initially. Next slide, please. So when the signal was used, or when the various frequencies were used to detect the damage inside the corroding rebar, if you see on the left hand side, the signals did not change even after 9 days of accelerated corrosion. But what, and similarly on the left hand side, the box shows there is some signal which is rising, but not to that extent until fifth or sixth day. So initially, for 1 to 9 days, when we were monitoring, we were trying to monitor the beam which is subjected to accelerated corrosion. We found out that guided waves were very good, working very nicely in the faster or the later stages when the corrosion had exceeded a particular level, but not on the initial stage. Next, please. So this is the visual picture, or the picture of the beam at various stages. Day zero means a healthy beam. Now it is, the tape shows the acoustic sensors have been put. If you only see visually, we will not be able to see anything until 7 days. The corrosion is very high, at 30 volts it was done. Next, please. But when we, and similarly we plotted those, that what happens. So if you see, there is one frequency chosen, a low frequency mode, which is not showing any change till 5 days. If a high frequency mode is chosen in ultrasonic, it is not showing a change till 7th to 8th day. So we are not able to, but in the 7th day, we see that the crack has already appeared on the beam. So that means this active system is not going to work. So then we had already installed the AE sensors and recorded the acoustic events also. Next slide, please. So this was the setup, the same setup which I have shown. The AE sensors, they are piezoelectric sensors. 6 sensors are put on this 1 meter beam, almost 700 beam, 3 on the front and 3 on the back. And then there's a preamplifier which amplifies the signal. And the AE setup, it's a system which, it's a data acquisition system which filters the data, and then it's shown. Next, please. So what did we get out of this? This is the actual real-time record of the beam when it is actually being corroded. So day one, we see 1 to 2 dots. Day two, day three, and four, we see rise of such number of red dots appearing. And we could easily correlate on the day five. We see minor crack and a similar streak of red dots on the screen when we recorded those AE events. So this is a typical AE hit plot. So initially, day one itself, we start seeing some things happening inside. So AE could easily pick up the inside cracking much before it is visible on the screen, much earlier than it is visible physically. That's the basic aim. On the other hand, the ultrasonics were not able to detect those. There was no change in the ultrasonic signal. What we expect is that the ultrasonic signal, as the bar corrodes, it pits, the signal should fall, but it was not happening until 7 days. But A was started working right from day 1 to 2, and we could see some A hits. The next slide. So when we plotted the cumulative A hits, this right hand side graph shows the comparison of only 5 days. Up to 5 days, what's the scenario? The scenario is the red line is the ultrasonic voltage, neither rising nor falling. HCP means potential measurements. Definitely, when the corrosion starts, there is a fall in the potential. But then this is a very qualitative parameter. You cannot relate to the, because it is dependent on so many parameters. So half cell potential, though well established, is a very conventional technique. You cannot quantify the corrosion or the damage with this, specifically corrosion. If you see the green line, that is the increase in the number of AE hits in the first 5 days. So this small picture of the activities which we recorded with the 3 kinds of local monitoring setups could show that A was much relevant in the initial 5 days of accelerated corrosion in comparison to our ultrasonic or even HCP. HCP is not a very good parameter. It's just a qualitative indicator. Has so many other parameters associated with it. So next, please. So the passive AE hits, the passive AE technique, We plotted for 9 days. It shows consistent rise. One parameter is A hits or counts. The other is the area under this curve, the A signal which is recorded. That is called the cumulative signal strength. That show a consistent rise from the day one. Three lines indicate three different samples. So it was quite a repetitive phenomena. Started with small samples, but we'll see in the further slides that how it has beautifully explored the various damage mechanisms in various kinds of structures, not only corrosion. Next. And not only this, so if this is the final picture which we are showing for the hits, the colored dots, they show the appearance of various hits at various days. Day one, 0 to 1 is first day. Those hits are appearing. Then second day, 1 to 2, 2 to 3. So we see that consistent rise in the AE hits. And the amplitude of the AE hits, this graph, it also indicates quantifying the damage level. So the initial 1 to 3 days, if we see the average amplitude of the hits is around 45 to 50 dB, whereas in the later stages, it shifts on to 65 to 75. So that a parameter, if we are somehow able to record that number of events and their amplitudes, we can also get an idea what is the level of the cracking or the damage in the structure. So AE has some beautiful parameters wherein we can not only see that there is some problem happening inside, where it is exactly happening, we can localize that using a 3D plotting event. We can do that 3D plots, and also the amplitude of the AE, it's an indicator of the quantify the damage happening inside. Next, please. So this is just for a beam which has undergone 9 days. We extended to various other samples, extended the corrosion for maybe large number of days. Finally, when we stopped, so we could see that AE events or AE hits, they could not only, so that if you see 0 to 10 days, the rise signals are continuously rising. That's the initiation, a micro cracking happening inside. Then there is a micro cracking which is coalescing together to form macro cracks in the calm phase or the phase two. So when we plotted all these events and joined them, we could see that there are four stages in the life of a corroding structure, and we should be stopping or repairing or looking into the structure right till the phase two. So phase three, it means now the structure has almost all the micro crackings or micro ones are coalescing and forming macro cracks, which will not be helpful to us. So basically, when we did this entire phenomena, we could make out where to stop. I mean, where we should be repairing our structure. So these AE parameters are useful in that. Next, please. Similarly, as I said, the CSS, cumulative signal strength, if we plot, we could see a sudden jump at two places called the knees. That's an indicator. As I said, initiation phase, when this jumps up, that means now the crackings, they will be becoming visible. Crack two or the second knee is an indicator. Now that inside that you are able to see that crack has come up to the surface. I mean, it's a huge crack which has appeared, and we could make out these phases correlate well with the dots which are appearing on the screen and we're seeing every day. So when as we're monitoring the beams, so A was very beautifully is not only beautifully picking up the onset but also the progression of the corrosion. We can make out now at knee one there is some major micro crack which is going to form and coalesce to form a macro crack and number of such cracks, and there's a sudden rise in the signal strength second knee, which indicates that this beam has given up. Next, please. So this is how the screen appears like it's an actual beam with actual record at the instant, like 9 days of corrosion. A transverse crack is appearing visually, and we are also seeing that. Next. So there are 3, 4 such slides. This is the actual state of the beam after 19 days. There were two cracks, and if you remove the visual and you see the other AE plot, we could make out the AEs could detect those things. Next, please. And this is the final corrosion pattern which we obtained, and we matched it with the visual as well as some other tools we also used in conjunction with these tools. But AE could give us very beautiful indicators of the various events which we are seeing, and probably that will help us to timely remediate or repair the structure. Next slide. Next, please. So this is how it looks like. This was the condition of the bars, and when we did the stress strain plots or we did the tensile stressing of the extracted bars of the various samples, we could see that This is a simple stress strain curve of the extruded samples after corrosion. There's a control sample, then there is an S9 means 9 days corrosion, 19 days. We could see the load carrying capacity drastically falling, the area under the curve drastically decreasing, though the initial stiffness of all the samples is same, which is very well indicating us that it's very important that they indicate a good stiffness initially. All the beams or the bars are behaving nicely initial stages, showing a good stiffness, but they have drastically lost their ductility. So it is so important that in initial stages itself we are able to pick up the damage and repair it. So this just shows that what kind of a damage on what it's so important to manage the damage at initial stage, and A definitely works very nicely into that. Next, please. This is just an example that how AE has been used successfully to monitor corrosion. Very well established now that corrosion is very well picked up, or initiation is very well picked up for by AE. But then there is one problem in this. The corrosion detection is very easily cracking taking place, but it may not be a very reliable tool when the structure is already cracked so much. So when it's profusely cracked structure, A may not work. That means if I take A as a tool to detect the initiation, that's very fine. But if you have already cracked structure and you expect and it's already profusely cracked, A may not work very nicely. So the conjunction or the synergistic combination of various tools is very important. Maybe we can use A for measuring initiation, and progression can be picked up by various tools. One of it may be ultrasonic or other things. So the combination is the key. Yes. So just one example that corrosion detection is very easily tracked by, or very well tracked by acoustic mission. Next slide. We also did this exercise that we did small samples, then we repaired a larger 4-meter size samples. We corroded first of all them to different days, like 10 days, 20 days, 30 days. It's a 4-meter huge beam. We knew that we could pick up corrosion with acoustic emission. We also tried to repair them. Next slide. These large beams, which are actually practically 4-meter size beams, we repaired them with GFRP. So it was if you see the cross section on the left hand side, the repair strategy was a U-shaped repair in the middle 2 meters out of the 4 meters. The damaged concrete was removed. Micro concreting was put in B part. Grinding was done so that the corners are beveled, and you can put the FRP wrap. Primer was put and FRP wrapping was done. On the left hand side the repair strategy is shown. So the 4-meter beams were repaired. Next slide, as shown in the next slide. And this is the slide what it looks like, the beam looks like. This 40 C40 means the sample has been corroded for 40 days and repaired with GFRP in the middle 2 meters. Why GFRP? It has been well established in literature that FRP not only enhances the load carrying capacity of damaged structures to some extent, it works very nicely when the structures are corroded. It actually it helps it to restore the strength, specifically the corrosion affected structures. So it's not you may not have to repair the entire part, only a portion of it, but then you can easily rehabilitate that and get a very good result out of that corrosion repaired beam with GFRP. So what we did was we deliberately put the wrapping in the 2 meters and A sensors on the outside. So it's a 4-meter beam. So when we put the A sensors and now subjected to flexural loading, definitely if you see the graphs on the left hand side, the red one, the control samples are like blue. The dotted is the damaged 30 days, 20 days, and so on. And the dotted green is the load carrying capacity after repairing. Definitely with repair, we expect, and GFRP wrapping, there is a restoration in the strength and integrity. So, but when we saw the 30 days and 40 day sample, we felt that if you see the green curve, it is not, there's a huge gap between blue and green. Red is of course the damaged one or the corroded one. We are not able to restore when the sample is badly damaged. So when the corrosion has exceeded beyond a particular limit, there is no utility or utilization or no effect of even GFRP repair. And while we were doing the loading thing, we also monitored with AE sensors. Next slide. So what we saw that that the corroded beams C10, C20, 30, 40, when they were repaired and the acoustic signals were recorded, if you see C30 or 40, first outcome of the was testing was flexural testing was that even if the beam is very much damaged, hugely damaged, there's no point in repair. So you are not able to restore to even one half of it. Then second, when we recorded the AE signals, we saw that the AE could not only pick like the initiation of corrosion, progression of corrosion, but also could pick up the repair which is taking place, or restoration which is happening because of the GFRP repair. So how do we see that? If you compare C20 with R20, or the second figure from the top in the right hand side, we see that the number of events are increasing. And similarly, repaired C R30 and R40 we see compared to the control. That means the cracked or the corroded C40 sample. When you repair it and then you record the AE activity, there are appearance of AE hits. So the recovery in this integrity of the structure after repair also picked up by AE. That means acoustic emission can also be used when you are repairing the structures. Put the sensors on and they will give you an indication that repair is working, and it is working very fine. So there is a reappearance of some phases of phases which is happening. For example, C30, we are only seeing two phases, but then we see three phases when you repair it and you monitor under flexural routing. Similarly with C40 or C20. Yes, next please. So we just try to extend and see that even the AE plots, they could, if you compare C10 and R10, the number of AE hits after repairing has increased drastically. So AE can not only, so there's a reappearance of the phases after repairing, well picked up acoustic emission. AE XY plots, they are telling you visually that after repairing, you are still able to hold, or it has effectively restored the integrity of the beam. So that can be picked up by AE. This is second example wherein AE was not only working for corrosion detection, initiation, progression, but also corrosion affected and repaired structures. They could be monitored with acoustic emission. And the last one, the last case study I'll present is next, please. This was done by my student. It is also a large scale beam, 2 meters beam. But the difference in this was we put the AE sensors onto this beam. It is a steel reinforced beam. And in parallel, we changed the beams to GFRP. That means FRP reinforced bars, or FRP bars we have used. Next slide. So just an example. So we have three samples. So the percentage of reinforcement is shown. They are using steel and GFRP. We compared the cracking modes or failures of steel reinforced and GFRP reinforced beam. Next slide. So AE could also monitor the variation in the failure pattern or cracking mode of differently reinforced RC beams, one with steel and one with GFRP. Here you see something called a speckle pattern. We deliberately put it there because not the tape shows the A sensors, 6 sensors, but the speckle pattern has been put because we were taking the pictures also side by side, and we wanted to correlate with digital image correlation, the comparison of visual A image and the DIC image. Next slide. Yes. So if you see the two graphs on the bottom, the left hand side is for the steel and the right hand side is for the GFRP reinforced beams. So very well we understand this. We could make out or variably put the three level of damages which the two bars or the two types of the beams experience. If you see the area under the steel reinforced beam, it is a ductility, it's a ductile behavior, whereas on the right hand side, it shows a the load carrying capacity is very high in comparison to steel reinforced beam. The deflections are larger, 70 mm in comparison to 50 or 55 mm, extreme ultimate deflection in steel reinforced. But the problem is that the ductility is compromised. It's a kind of when we when we subjected them to flexural loading, the load deflection curve shows that the failure has been in steel reinforced, it's a ductile failure as we expected. And on the right hand side, the GFRP reinforced beams, they showed a brittle sudden failure kind of thing. The kinks which we see in the graph, they are the slipping of the FRP bars. They were glass, they are GFRP reinforced bars. So next slide. So when we put the A sensors, and these are the typical crack patterns I'll discuss later. Next, please. So this is the AE activity recorded for the two types of the beams. So if we compare the AE activity, the number of the amplitude of AE hits is larger. Amplitude is larger in GFRP. It has a larger load carrying capacity but a lower modulus. But then it fails by sudden cracking, and that is also picked up by acoustic emission monitoring or AAT technique. So the and number two, if you visualize the A hits, the initial phase is very long in GFRP, but then it suddenly fails. Whereas in steel reinforced, the initial phase is very small, and it suddenly, it then steadily rises. But that initial phase is very long, and number of hits are very large, and because of its performing good initially, but then suddenly gives up. Next slide. So if I give you the key insights, the cumulative A hits or even the amplitudes, they indicate how the cracking is happening inside the two. These are just some things which I've already said. That the initial phase, large number of hits is there in the GFRP reinforced beam, lesser hits in the steel reinforced beam. Even the amplitude in steel reinforced beam is lesser, larger in GFRP reinforced beams. But and the initial phase of taking the load carrying capacity, because of its high tensile strength, it is prolonged, but then it fails suddenly. Next slide. So I'll show you three pictures probably. This we can skip, just in general discussion. I will share my PPT if required. So the insights is, then there is one parameter, average frequency versus rise angle. If we plot this, we are able to see how the damage is progressing. So if you see the dot on the SR or the steel reinforced beam, it shows the average. So what we are doing is an average frequency plot, that is over 100 A hits, that average has been taken, that value. So steel reinforced beam, if you see the damage level 1, that means the initial phase, it fails in tension, whereas the GFRP reinforced beam fails in shear. Next slide. If you increase the load, again, the average frequency has risen for steel reinforced beam. It is still failing in tension, but the failure of the GFRP reinforced beam, now this is an AE value. This is a parameter from acoustic emission. Average frequencies versus rise angle. So this parameter could indicate initially steel reinforced beam that failed in tension, and GFRP reinforced beam failed in shear. Whereas we increase the level of loading, the shift is taking place. Again, it is tensile and steel reinforced, and in the GFRP beam, the mode of cracking is changing from shear to intense. So dot is shifting. Next slide. So now see, it has crossed. So simultaneously, we're getting the values, these values. So damage level 1, 2, 3. So steel reinforced beam will always fail in tension. And the final failure of a GFRP reinforced beam, the dot has shifted towards the tensile phase. So initially shear and then shifting on to. So the context is this, that the AE parameter, various parameters, this is just one of the parameters, they not only indicate the rise of the activity, doesn't not only indicates the increase in the damages, but there are some other parameters which can demonstrate or classify the kind of cracking which we expect in the structure and type of failure mode it undergoes. Next slide. These are last three slides, which shows a comparison of some normally utilized techniques. Like visually what we see, this is the stage 1, level 1. We are well into the elastic stage of the structure of the beam. The second picture shows the digital image correlation plot. It's a longitudinal strain profile. And the third picture shows the AE activity. So, well, if we compare the three, we are able to identify, and all of them matches well. Visually, we are not able to see anything. A DIC gives you a small, change in the color, which indicates that there is change in the strain profile. And A is able to pick up exactly where we expect those red dots, which are correlated with this image. Next. This is the progression in the intermediate stage, phase 2, damage level 2. Well, we see the deformations in the structures in the actual beams also. The DIC images also show how the cracks are progressing. And the beautiful picture at the bottom shows the AE profile or the AE head plot. So acoustic emission can So this just graph, this picture just shows, or this comparison just show, and how AE is able to pick up. This is just a simple flexural loading. Next slide. And this is the state at the final. So where we expect the cracks to occur, of course, it's a tensile failure in a steel reinforced. At a sudden failure, a big crack is observed in the GFRP reinforced beam on the right hand side, and the AE plots are showing exactly where we expect or where we see the failure finally taking place. Even DIC is showing the correct thing, but AE gives you the dots. You are seeing the dots appearing on the screen. So the beauty of A is this. But then if you have already damaged structure to a large extent, and then now you expect that A should, it should pick up those, it may not work at a very later stage when the deterioration has exceeded beyond a repairable limit. So A has a beauty of picking the initiation of damage, and then you can take a decision of timely repair and remedify the structure, and this may work. So that ways this tool is a tool for structural health monitoring in the initial stages, and proper timely measurement or maintenance repair strategy can be looked into. Thank you. I just showed in my presentation three typical cases where the AE has been applied and it has worked well.
Thank you so much, ma'am, for your informative session. I really like the correlation between AE and all other technique, the DIC one.
Thank you.
Now, floor is open for question and answer.
Yes.
They will be handled on first come services. So please raise your hands if you have any questions in the audience.
Yeah.
So, I just want to know that this acoustic emission will help on that type of structure also, whether we want to do the structure audit for a whole building in one go.
So that means you need to have an array of sensors. So typically, what we where we use AE, we looking for a structure where we can put that array and monitor it from a remote location. You can do
Remote.
it real time, yes.
Yes.
But we need to put the sensors, and also we need to have people who can read those sensors and digitize the data, and you're able to quantify that. So
Mhm.
now there are some setups which are coming in the market, wherein it's just a small device which you just put, and but those AE sensors have to be there. So
Okay.
earlier we used to have very huge setups for that, very
Mhm.
large number of cables going into our areas where we are putting the server rooms. But
Mhm.
now those systems have reduced. So HCP is fine. It's see, if the first step will always be, I'll go in for measurement of half cell potential to
Mhm.
understand that there is a likelihood of the corrosion or which has taken place.
Yes.
And then to further, if I know that there's a problem area, I'll have to use a local tool like acoustic emission and keep on monitoring over a period of time so that I'm able to repair it at the right stage.
Okay.
So my first indicator always will be my electrochemical measurements. That there
Mhm.
is no doubt about it. But then if I want to quantify and take a decision, make a decision whether to repair, what kind of repair, and when to take that repair decision, that has to be quantified. So that has to be taken care of by a proper parameter. Probably these tools will help us in that.
For that we need to place this acoustic emissions system
Yes.
permanently from at the site,
Yes,
so
sir.
that we get the data, and accordingly we plan the repair and retrofitting things.
True, true. So, like historical structures are very, are very important monuments. They're already putting up these sensors and recording it sitting at their remote offices. So, there it is very important to take these decisions. This is one of the drawbacks also. Now, here the ultrasonic or other tools will come to the rescue. You may take signal, go back, and you may come after, say, 1 year or maybe 6 months and take the signal again. So, you can just compare your two signals. So, there the active tools may work nicely in general kind of buildings, but wherever it's a very important structure, we need to put the systems in place. For example, this sensors.
Okay, thank you.
We hold such talks every month. And if you want to join the Indian Structural Health Monitoring Society, you can just Google it, and you can just go to the website and fill up the application form. Thank you very much.